In this video, we're going to begin polynomial prime factorization. And let's talk about what prime factorization means when we're looking at polynomials. Recall that there's a difference between a factorization and the prime factorization. For instance, here's a factorization of 12, but it isn't the prime factorization because 6 is composite. Once we factor 6 into prime factors 2 and 3, then we have the prime factorization of 12 because all of our factors are prime. The same idea applies to polynomials. For example, here's a factorization, but you'll notice our first factor still has a greatest common factor of 3. Once we factor that common factor of 3 out, we have a prime factorization because all 3 factors can't be factored further. Here's another example. We have a couple of binomials. This second binomial is prime. We can't factor this any further, but notice the first binomial is the difference of 2 squares. We can think of this as x squared minus 3 squared, and factor it to x minus 3x plus 3. Again, our third factor was already prime, so we didn't have to factor further. As a check, I'll look at each factor individually and see that all of them are prime, and so I now have the prime factorization of the polynomial. The first technique we're going to look at combines grouping and the difference of 2 squares. So first, you'll have 4 terms, and you'll have to factor that using grouping. Then, one of the factors will not be prime, it'll be composite, and you'll have to factor that binomial further using the difference of 2 squares. Here's the first one. See how you do. Since I have 4 terms and all 4 of them do not share a factor in common, I'll shift to grouping. The first 2 have a common factor of x squared. The second 2 have a common factor of negative 4. I can factor out the greatest common factor of the quantity x plus 1. And now I notice that the first factor is prime, but the second isn't. This is still the difference of 2 squares, which I can factor to x minus 2 and x plus 2. And again, the order of these factors isn't important since multiplication is commutative. Here's the next one. The first 2 factors share a y squared. The second 2 share a common factor of negative 1. After factoring out the common binomial, the second factor is still composite. I'll think of that as y squared minus 1 squared, and factor using the difference of 2 squares. Try this one. Our first 2 share a common factor of x squared. Our second 2 share a common factor of negative 9. Now they both share a common factor of the quantity x plus 1. And once that's factored out, I notice the second factor can be factored further into x minus 3 and x plus 3. How about this one? The first 2 terms share a common factor of x squared. The second 2 share a common factor of negative 1. I now factor out the binomial for x minus 1. I'm left with a composite factor of x squared minus 1, which is the difference of 2 squares and can be factored to x minus 1, x plus 1. And here's our last one. Our first 2 factors share a common factor of 25t squared. The second 2 share a common factor of negative 4. Once we factor out the GCF of the quantity t plus 1, our second factor is composite, and it's the difference of two squares. I'll think of this as the quantity 5t squared. I'll think of this as 2 squared, and so it'll factor 2, 5t minus 2, and 5t plus 2. Well, that concludes this video where we've began prime factoring polynomials, in this case using grouping and then the difference of two squares.